The following program is brought to you by Caltech.
Good afternoon, everyone, and thank you very much for coming. My name is Jason Rabinovich, and I'm a fifth-year PhD student in Dowsett here at Caltech. I'm also one of the student co-leads for the 2013 Caltech Space Challenge. So the Caltech Space Challenge is a very intense 5-day mission design competition where we invite 32 students from around the world, bring them to Caltech, give them a series of lectures, and we supply them with mentors who are professionals in the field, and we challenge them with an extremely complicated mission design problem. This year, they've been tasked with designing a human mission to a Martian moon, and we've only given them 5 days to accomplish this. Right now, the teams have worked extremely hard the entire week, and the competition culminates with each team giving a 1-hour presentation. We do ask that you hold your questions until the very end of the team's presentation, where they'll all come up to the front here and be able to answer questions for you. And with that, please join me in welcoming Team Explorer.
Hi, everyone. I'm Nick Sweet. I'm going to introduce our project. So we are Team Explorer 2013. Our project name is TAPER, the Technology Advancing Phobos Exploration and Return Mission. So we've been inspired in a huge amount throughout the week, and one of the key quotes that came out to us was, "He who receives an idea from me receives instruction himself without lessening mine, as he who lights his taper at mine receives light without darkening me," from Thomas Jefferson. Obviously, the parallels with the Caltech symbolism also are pretty apparent. So this is exactly what we'll be presenting to you today. Chris is going to talk about our execution and administration structure. Abigail will talk about our science. Natasha will start off our engineering with a mission profile about launch dates and trajectory. Franz will give a description of the spacecraft design and layout, as well as our propulsion systems launch requirements. Stephanie will then give out our human factors, and I will conclude our presentation. So without further ado, Franz, if you want to get started.
Our mission is going to be planned to be encompassed by the policies under the Global Exploration Roadmap laid out by several space agencies already, which basically means that currently we're in low Earth orbit, and technologies will be developed along the way to Mars through demonstrations on the Moon and Martian moons. The key technologies for our mission that need to be developed are decrease in satellite size and increase in capability, heavy launch lift capability, composite propellant tanks, and boil-off technology. Before our manned mission, we plan to send precursor missions that will give us science data on the topography, gravitational field, radiation, and composition of Phobos, which we'll talk about why we decided Phobos. And after our mission, our mission is essentially a stage to land humans on the surface of Mars. So that's kind of where our mission fits in a broad spectrum. Our mission statement is to land a crew of 4 people safely to the surface, to land 2 people to the surface of a Martian moon, 4 people in the vicinity, as a precursor to Martian surface exploration. Key objectives in this mission are to return samples, determine the feasibility of in situ resource utilization of Martian resources, and determine the evolution and origins of the Martian system. Our timeline for the mission starts around now with technology demonstrations with specific precursor missions in October of 2024 with a fallback contingency date of the next opportunity to go to Mars in 2026. And our manned flight is planned for the low-hanging fruit in 2033 with a backup date of 2035. So this is a big picture of our system architecture. For our mission, for the manned mission, we require 4 SLS launches for propellant, 1 Falcon Heavy launch for habitat and exploration vehicle, and 1 Falcon 9 launch for the crew. These will all assemble in orbit, transfer to the Martian vicinity into a Phobos trailing orbit, and from the habitat, we'll drop down to the surface of Phobos with 2 crew and come back to the habitat and then back to Earth. This is kind of a little bit more of a breakdown, giving some launch dates and kind of a time scale for what we're doing in each phase of the mission. Essentially, we'll have an assembly phase and then a transit stage, and then get to Mars and come back. And with that, I'll hand it over with Abby for science.
Great, thanks. So I'm going to talk a little bit about the science that we plan to do during our human mission to Phobos. So as Chris mentioned, we'd like to talk to you about why Phobos. And the reason we waited to tell you this is because a lot of this decision was driven by some of the science we're going to be able to do on Phobos. One of the most important reasons we decided to choose Phobos was one of our primary identified mission's goals, which was to investigate the Martian moons as possible sources for in situ resources. Phobos has been proposed to potentially have subsurface ice. The moon is very low density, so may contain some ice in the subsurface. There's also grooves across the surface of Phobos, which have been proposed to potentially be outgassing from volatiles hidden in the subsurface, which could be used for resources. Additionally, Phobos is geologically interesting. You can see that it's composed of 2 color units. We have this kind of bluish material on the rim of this nice impact crater. This is called Stickney crater. And we have this more reddish material that covers most of Phobos. Investigating both of these materials to see their compositional relationship is important in helping us understand the origin of these moons. Additionally, Phobos has this nice impact crater, which may expose things from the deep subsurface of Phobos. So some of the strategic knowledge gaps that we identified that would need to be addressed before we reached Phobos were touched on briefly, and they include things like mapping the global topography, measuring the gravitational field, assessing the radiation properties in the local vicinity of the moon, mapping and assessing the mechanical properties of the regolith, searching for subsurface ice and other volatiles, mapping the thermal environment, and making a global mineralogical and chemical composition map of Phobos. These sorts of science goals can all be achieved by missions that include remote sensing instruments, such as high-resolution imaging systems, spectrometers, neutron spectrometers, radar, and some of these needed to be achieved by kind of in situ science, but we felt could be achieved by the deployment of small, relatively cheap satellites. So overall, we felt that these strategic knowledge gaps could be achieved by relatively inexpensive orbiter with some in situ science missions to Phobos. So the main science objectives that we derived for this mission were drawn upon from the main mission objectives. So this first one is to investigate the origin and evolution of the moons in order to better understand the Martian system. Now, in order to do this, the primary goal that we'd like to achieve is to really understand the composition of Phobos. This is still very poorly understood. Remote sensing data has not really given us any definitive composition, and we think that the composition may be a link to the origin. There's 3 proposed origin scenarios for the Martian moons, either formation by a giant impact onto the surface of Mars. It could be a captured asteroid, or perhaps the moons co-accreted in the same time that Mars formed. Each of these scenarios implies a distinct composition, and so by able to measuring the composition in situ, we'll be able to answer this question. There's some additional science questions that we can address in order to further constrain this objective. A second objective is to assess the availability of in situ resources on the moon for possible future use in manned missions. This is an objective that relates directly to the global mission architecture of this entire program, this idea that Phobos is a stepping stone to Mars for manned exploration. So in order to do this, we'd like to determine the volatile content of the moon's surface and subsurface, and also see if we can detect and quantify any mineable material, including, but not limited to, magnesium, methane, ammonia, clays, rare earth elements. Finally, we'd like to understand the current environment of Phobos in the context of the Martian system in order to support an architecture for future Mars missions. So this includes understanding the radiation environment and the dust environment around Phobos. So in order to achieve these goals, we developed a science traceability matrix that I won't go through in detail, but we took our mission objectives, we related them to measurements, what those measurements would require, and that allowed us to develop a payload in order to address all of these science objectives. Before we developed the payload, we also thought about where we'd like to land, and we identified 3 landing sites, and the number 3 was constrained by engineering requirements. The first landing site would be somewhere in the vicinity of Stickney. There may be material that's exposed from the interior of Phobos that's present in Stickney. The second is this landing site over here on the rim of Stickney, and this actually corresponds to that bluer Phobos material. So this will give us the opportunity to sample one of these potential compositional units. The second landing site we identified is up here, and this is in kind of the redder material Phobos. So again, this is a different environment on Phobos. Finally, a fourth landing site is noted, and this is a landing site where we'll eventually park our habitat vehicle to leave on the surface as a resource for future manned missions to Mars. So here's a summary of the kind of science payload that we'd like to bring to Phobos in order to address our science. Developing this payload, we thought about what instruments were needed in order to answer our mission objectives, and also how best to maximize the amount of science we could do during a short stay mission, and also maximize the fact that we have both humans and robotic resources in order to explore the moon. So our first objective, a science payload, is sample collection equipment, and this includes things like drill cores and scoops and rakes in order to pick up rocks and soils and cores that go into the Martian regolith. The second kind of instrument that we thought about were these mobile science platforms, which we dubbed Phobots. And the idea of these little Phobots would be to load them up with a suite of in situ instruments, and we have a recommended suite that would include instruments that would help identify the composition and also image the surface. And the goal of these little Phobots would be to provide a broader context for the samples that were being collected by the astronauts on the surface. So these Phobots could travel perhaps greater distances, examine more samples. Perhaps they could find a sample and identify it as something interesting for the astronauts to go collect. And these Phobots could also be controlled by the astronauts who remain in the orbiter above Phobos, which we'll discuss later in our mission architecture. So these two combined we're really proposing would help utilize the connection between both humans and robots on the surface. Additional science instruments we'd like are a seismic array, and this idea is to deposit several chipsats as we descend into Phobos. These are relatively inexpensive and light detectors that we can use to set up a seismic network to monitor Phobos' interiors. We'd like to set up at each of our landing sites a space weather station that can measure the radiation environment. And we also decided to leave some mass margin for some science yet to be determined. We wanted to give ourselves flexibility to change our science payload based on what the precursor missions found. So for example, if we send a precursor mission that detected subsurface ice at depths that could be reachable by a drill, say maybe tens to hundreds of meters, we'd like to be able to bring a drill that could reach that surface. If we don't find that, we thought of some other kind of fun science ideas that we could do, including setting up observatories on Phobos to look at Mars or to do some sort of radio-type astronomy. And here's just a table summarizing for our mission objective requiring mission suite the sorts of mission instruments that we would require. So our strategy for sample collection was to require about 100 kilograms of samples to be collected from the astronauts. This includes about 30 rock samples from each EVA site, 10 core samples, and 5 scoop samples. We also wanted to include a mass margin for additional samples to be collected for educational public outreach, international cooperation, and any targeted opportunity samples that we found. A side note, we need to think about the containment and planetary protection issues in collecting these samples. We will use equipment that has been planetary protection compliant, and we will also store at least the cores in cryogenic containment in order that none of the potential volatiles that are in them won't react with the sample as we bring these back to Earth. So here's a timeline for surface operations. This is a timeline that could be expected if, say, we discover that we want to bring a drill with us to do a deep drilling at one of the sites. And so what we would do is we would land, we'd spend a couple days setting up the drill, collect samples at a couple sites, move to the next site, set up our weather station, collect some more samples and drills, and spend about three or so days at each site collecting samples before we leave after about 24 days. And we really found that we could do an incredible amount of science in just this 24-day period. In addition to the in situ science, we also considered the science that we could perform kind of along the way and while we were docked at Phobos. So to that end, we decided to include a small remote sensing package on the orbiter that will remain in orbit around Phobos during our mission. And this will include a high-resolution multispectral imager. So this can be used to image the surface of Phobos, which is useful for public outreach if we want pictures of the astronauts on the surface. As well as science goals, a radar that may be able to better determine with better spatial resolution than the precursor missions any potential subsurface water ice, some particle detectors to assess the radiation environment, and a fleet of CubeSats that we'd like to send to Deimos. We think the science return that we could get from addressing the answer to the question, how are Phobos and Deimos compositionally linked, would be very high, and the cost of that science return, if we're already in orbit around Phobos, would be very low. So this is a very favorable option we would like. We'd also like to have a dedicated instrument, got cut off here, for education and public outreach. This would be an instrument that perhaps the public could propose to put on the orbiter, or maybe a type of camera that the public could help pick pictures they'd like to take. Finally, we considered science that could be done in transit, and one of the ideas that we were really excited about with this idea for astronauts, at least on the way back, to start compositional analysis of the samples they've collected. The idea behind this is that we'll have the ability to collect far more samples from Phobos than we may be necessarily able to return to Earth. So if we collect our specific amount of samples, say 100 kilograms, seal those off, put those to the side, and then let the astronauts play around with the extra, say, 100 kilograms of samples we collect, in order to look for anything that could be potentially interesting, maybe a sample they really want to bring home, and set up science maybe that will help instrument sample curation facilities examine these samples once they bring back to Earth. We'd also like to do some radiation experiments, including this experiment here, which we called New Life, and this is modeled after the experiment called Phobos Life, which was on the Phobos Grunt mission, which was a very small little container here that had microbes and was supposed to assess the survivability of microbes in the Martian environment. And this is also a great instrument to get public outreach and cooperation. We're going to work with the human factors to do some experiments that will test human reaction to the space environment. And also think about outreach opportunities for the general science community to propose experiments, develop instrumentation for observations of Earth as an exoplanet.
So now we're going to begin talking about the engineering side of things, how we're actually going to make these science objectives happen, and how we're going to get there and get these humans there back and bring them home to come safely and actually perform a lot of these goals and objectives that we set forth by these science people. So this is not really a trivial task. It's very difficult to bring people there and back. So we've assigned these top-level requirements that we want to achieve. We begin with just bringing them back home safely. So as much as we would like to just leave them there, we can't do that. But we have to bring them back, and it becomes a difficult engineering task to do this. So they have to go there, they have to come back, they have to land on the surface. We want people to touch the surface. We want this to be kind of a action that inspires people to know that humans have been to another body that we see in the sky. Maybe not from here, but through a telescope we can see it and say that we've been there and we've actually touched that surface. Again, the science goals are a big driving factor. There are a lot of things we can find out about our universe and just about how everything was created here in our local neighborhood. And then we want to demonstrate a lot of technologies as well. This serves as kind of a precursor to where we want to get, which is to Mars. We can demonstrate a lot of technologies for how we want to get to Mars through this mission. And from an engineering standpoint, it serves almost as a logical step in this progression to eventually get people to Mars, which is what we want to do. Finally, we have to comply to planetary protection. We don't want to put as much, human contamination all over the place as we can, because then if we get to Mars and we discover life, we might just be discovering ourselves, and that's not really interesting for anybody. So there are a lot of subsystem level requirements. So these are the trajectories, the spacecraft designs, propulsion system, human factors, all that fun stuff that we're going to get into. So we will hopefully keep you entertained with that, because it gets pretty exciting, some of the things that we try to do with this.
So before we begin the trajectory design, first we need to choose a launch year. So in order to do that, we corresponded the solar cycle, shown here in orange, thanks to a graph that was presented to us by Josh Hopkins. We see a solar maximum, so as little galactic cosmic rays as possible, during the years 2033 and 2035. We notice that 2033, if we choose that as the selected crew launch year, it gives us a backup of 2035, just in case anything requires us to postpone the mission towards the next opportunity. So we'll show the trajectory for the selected nominal launch year of 2033, but keep in mind that we also have some comments about if we were to do this in 2035 in terms of sizing delta V requirements for the propulsion system, and so on. So first, for selecting the particular launch date in 2033, what we did was consider every day within the year 2033 and a variety of times of flight between 100 days and 1 year. We looked at various parameters, and the most important for this is looking at the total delta V. So this graph that we see here on the left is constructed as a simple initial approximation to give us an idea of a good date to leave. Simply connecting using a Lambert arc the locations and velocities of Earth and Mars. And it's just an approximation, since we'll actually be in orbit about those two bodies. What we notice is the total delta V, so the beginning and end of that Lambert arc. We see a local minimum that occurs here for low launch dates, times of flight. In particular, in this white box, we can see some interesting times of flights and departure dates. So we arbitrarily picked a time of flight of 180 days, which corresponds to an Earth departure of the 7th of April 2033. On the right here, we see the corresponding Earth departure C3, which helps us understand the launch window that we can use. So for 180 days after Earth departure on the 7th of April, we will arrive to the Mars vicinity approximately 6th of October. We assumed that 1 day prior to the the LEO departure date, we would want to launch into that LEO orbit, although we could change that and leave earlier. So we estimated that the crew will launch on the 6th of April 2033. We also included an Earth departure window, which was chosen keeping the time of flight to 180 days. We looked at the delta V total, so just a horizontal line in this direction, and we placed a constraint of a total delta V of 6.8 kilometers per second, which seemed good for the propulsion sizing and still allowed extra margin just in case of any uncertainties. So we estimated a departure window of 1st of April 2033, this is from the LEO, to 2nd of May 2033, or that could change depending on the upper limit that we'd like for the total delta V. For the return, we wanted a short stay mission, so we considered returns that occur after our arrival into the Mars vicinity, so between 20 days after and 70 days after. We also considered times of flight for the inbound trajectory, so back to Earth, between 100 days and a year. We notice a local minimum here that occurs where this white box is shown for the Mars departure delta V. Recall that we will actually be considering a direct Earth entry, so we just want to look at this Mars departure delta V. So we approximated a time of flight of 246 days, which falls within this box, and we leave Mars 30 days after our arrival on the 2nd of November 2033. That would give us an Earth arrival of 6th of July 2034. We also see on the right here a plot of the Earth arrival velocity, which is just an approximation for each of these launch dates, arrival dates that we considered. So this white box corresponds to the same departures from the Mars vicinity as this white box, And we notice that the Earth arrival velocities are approximately 11 kilometers per second, which are reasonable for re-entry vehicles. So just as a backup, we can do the same analysis, and I'll just briefly cover this. Within this white box are our possible departure dates and times of flight. So we kept a 180-day transfer to Mars for the backup 2035 crew launch. We leave Leo on the 14th of August and arrive to the Mars vicinity on the 10th of February with a launch date from Earth on the 13th of August. This gives us a short departure window using the same criteria as before of the 6th of August 2035 to the 20th of August 2035. And similarly, we would have a return trajectory that is 233 days on the way back, which would bring us leaving Mars on the 11th of March 2036 and arriving to Earth on the 30th of October 2036. So now we can get into the interesting trajectory design. So when we look at this, we want to start from the bottom and move our way up. So as said before, we would leave Earth on the 6th of April 2033 or before, and from Leo, we would perform a delta V of about 3.7 kilometers per second on the 7th of April 2033. We assume this Leo has a 300 kilometer altitude, and this would inject us into the interplanetary transfer orbit, which was estimated to have a C3 of 8.4 kilometers per second. And for 180 days, we would find ourselves in the vicinity of Mars, which we would then perform a plane change and insert into a high Mars orbit. The high Mars orbit has a periaps, which is about the Phobos radius, about Mars, and an apoaps that is beyond the Deimos orbit. So this would allow us opportunities for flybys, which we identified as favorable science. So this plane change and insertion would occur on the 6th of October 2033 with another delta V that is quite large. So these two delta Vs drive our mission design. In addition, we would find ourselves in the vicinity of the Phobos, so we would try and work our way into an orbit then. So we'd perform a periaps raise and then an apoaps lowering to get into a Phobos orbit. And these are small delta Vs in comparison, and we would find ourselves in a Phobos L1 Lyapunov orbit on the 7th of October 2033. Our rationale for choosing an L1 Lyapunov was that the landing sites appear to be on the side of Phobos that is facing Mars, and since the L1 Lyapunov lies between the Mars Phobos, between those two bodies, this will be favorable since the crew that aren't landing on the surface of Phobos could communicate with the crew that are landing on the surface of Phobos. We also chose an approximately planar trajectory with respect to the Phobos orbital plane, just to help us reduce any kind of maneuvers that we would need to maintain that orbit over 30 days. So then if we come back from the L1 Lyapunov, we would perform kind of a mirror trajectory back, raising our apoaps and lowering the periaps so that we could insert into approximately the same high Mars orbit. And then we would perform a plane change and inject back to our to Earth so that we would have a direct Earth entry by the 6th of July 2034. So in all, this gives us, for each of these impulsive maneuvers, a total time of flight of 456 days and a total delta V of approximately 13.5 kilometers per second, although we added about 1.5 kilometers per second of margin just in case any errors for abort scenarios that may be important, or just in case we decided to change the trajectory slightly. So just some pictorials so that we can see what these orbits look like. We would leave Earth from a Leo April 7th, 2033. We'd work our way this way until we arrive at Mars October 6th. We would leave the vicinity of Mars November 2nd, and we would travel back to Earth. And you can note that the orbit actually passes closer to the Sun than the Venus orbit, and this wasn't planned as a gravity assist, but future analysis could actually incorporate the gravity assist to reduce the total delta V. In the vicinity of Mars, we come in on this blue trajectory, and we perform a plane change around here, and we enter into this high Mars orbit, and we raise the periaps so that we're actually getting close to the Phobos orbit. And we enter and remain here for approximately 24 days with minimal maneuvering to remain in that orbit. And then after 24 days, we leave and we perform a burn, not at periaps or apoaps, but at a location that reduces how normal the delta V is to the actual velocity at this point. And this involves a plane change as well, and this sends us back to Earth. So just a 3D view so that you can see that we have to do the plane changes inbound and outbound hyperbolas in the Mars system. So next we will look at spacecraft design and layout.
So now we'll keep going with the engineering design. We're actually going to get into how we designed our spacecraft, some of the engineering process that we took to get there. You can see from this picture, we have a pretty good CAD guy that works with us, but we are going to go through how we decided to do this, what these vehicles are, and exactly our process for finding these. So to begin, this is our vehicle stack, so hopefully I can do this right. So we'll see here, we have the Phobos Surface Explorer, which you see on the bottom, which is a novel concept. It's a combination of a SEV, which is a space exploration vehicle, and a habitat, which we are creating. The idea behind this is we want to actually leave something behind on Phobos. So we're creating this vehicle, which will travel to Phobos, actually leave a habitat behind, but we'll get more into that when we actually talk about this specific subsystem. We are using the Dragon Crew vehicle. We decided to use this for a number of reasons. We think it has a lot of advantages, and we also like the idea of incorporating the commercial spaceflight people with other missions. We also use the Bigelow Deep Space Habitat. We save a lot of mass by using this. It's inflatable, and again, we like this cooperation type of idea of working with commercial people and providing an avenue for them into space, maybe beyond just LEO, with these bigger types of missions. So for our propulsion system, if you hadn't noticed, we have gigantic tanks and we have huge rockets, which is really exciting to design. So we are using nuclear thermal rockets, which are in the process of being developed, and which is the nice thing about designing for 2035 is we can kind of keep our imaginations open, and this is a technology we think is really enabling to one day getting to Mars, and is what we finally decided on using. But we'll get into that process of actually deciding to use this later on. Again, here are the three vehicles that are actually going to have crew in them. We have the Bigelow Deep Space Habitat, inflatable, we get it from commercial partners. We have the Dragon Crew vehicle, we get that from SpaceX. Again, we are incorporating commercial people with this. And then there is the Phobos Surface Explorer, where this front part is basically an SUV, and this back is the habitat, which we are planning to design ourselves specifically for this mission. So you see we have these claws on the bottom, which is what we'll actually use to attach to the moon itself. And this is mostly driven by the fact that the gravity is so low that you really can pretty much hop and you'll achieve escape velocity, which is not really good for wanting to keep something on the surface, but we address this with these claws that we attach to the bottom of our spacecraft and to the habitat. So again, here it is, and you can actually see the separation here for the two separate stages. So this bottom stage, the habitat, will stay on the surface. It'll also provide our astronauts, which are exploring Phobos, an additional place where they can go to after their daily excursions and rest, and then eventually after the time that they spend on the surface, they'll fly back with what we're calling the PSEP, which is the Phobos Surface Exploration Separator, something like that. I told myself if I could remember these acronyms, I would be happy with my presentation, so maybe that's close enough. But these are just some basic masses. Science instruments, we are at about a ton, so we want to do a lot of science. We think science is one of the big drivers and reasons that we want to go to Phobos. As we mentioned previously, there's a lot of interesting things to do there, and we want to enable this through our engineering design. So here, again, the big, nice picture to show you. We have Mars in the background. We have our Phobos Surface Explorer here, and then we have our deep space vehicle, which is in the background. So for the most part, the deep space vehicle is close to this Phobos Surface Explorer so that if they have to abort, they can go back to that spacecraft. And it also serves as a platform where astronauts can actually conduct some research on their own while there. The two astronauts that remain there. It serves a nice way for you to actually have this contingency of being able to go back and have people on board if you need to for the Phobos Surface Explorer to go to. Here you see when we actually leave the habitat behind, hopefully with no astronauts in it, and We go back and we fly back with the Phobos Surface Explorer Separator, and then we dock with the spacecraft, and as you saw in the architecture, from that point on we fly back to Earth. So now, after we've kind of decided all these things, we had to look at our propulsion systems, figure out exactly how we got to this design, and I'm going to try to guide you a little bit through our thought process for achieving this. So with this specific design, we need 6 launches, which is not trivial and was a surprise to us when we sized our mass, but this is what it came out to be, and we think it's something that's a feasible design and it's necessary for this flight. So we have a Falcon 9, which we would use to send our crew vehicle, which is the Dragon capsule. Then we also have a Falcon Heavy, which sends the Deep Space Habitat and the Phobos Surface Explorer. Then, to actually get these gigantic tanks in, we need 4 SLS launches to put this, 246 tons of propellant up to actually fly us into the near Phobos orbit. So the cost is pretty significant for those launches. We have it outlined here, and it's one of the main, tough things with this design is that the rocket equation is very unforgiving when you want to get somewhere fast. So the fact that we decided to choose the opposition class, which is the short stay, really limited us with our design, which we'll actually get into later. So here is our big mass budget. So what we decided to do from the propulsion standpoint for figuring out our vehicle and designing our propulsion systems was to get masses from everybody else and iterate upon that. So we got those masses. This is a general outline of those masses, sums, and this is all in metric tons. If anybody's interested to really see all these numbers, we're happy to discuss them afterwards. We added in a lot of margins with this for most of the actual hardware, the capsule, the Dragon capsule for the Deep Space Habitat, and for science, we added in margins of about 10% for the mass. And then we also, to add margins into our propellant, we actually designed our delta Vs for the 2035 opportunity, which is more restrictive. The end of a launch window of, I think, about 2 weeks of that 2035 opportunity. And then on top of that, to those delta Vs, we added another about 5% value, so we get a good margin to add to our, which filters down all the way into our propellant. So we did a trade study to decide how we wanted to propel our spacecraft. So we looked at the 3 big ones that you could actually use. I don't think there's an astronaut here that would want to take a solar sail all the way to Mars, so we didn't really consider that, but these are the 3 ones that we looked at. So there's chemical propulsion, which is used all over the place. It's what most space vehicles, all space vehicles are essentially using now. There's some electric propulsion being used. It's mostly for smaller devices or satellites. And then we also looked at nuclear propulsion, which is at lower TRL levels, but is being developed. So the main thing, these are the main systems we looked at. We looked at these references, which I have here to give us an idea of performance and to design with those values. So with these propulsion systems, we looked at multiple flight and rendezvous scenarios. And to give you an idea of this, we have the following examples of ones that we looked at. So the most simple one is to just go to LEO, rendezvous all of your parts together there, and fly away from there. So we looked at nuclear thermal rockets for this, to do this, and then we looked at a cluster of 14 50 kilowatt Hall thrusters. So as you can see, your travel time is pretty high when you're using these electric propulsion systems, which doesn't work well with our opposition class mission, because we don't really want our astronauts to die of radiation before they get there. The NTR actually did enable this, but as you can see, there's a lot higher mass there, but in order to achieve our mission objectives, we have to go with this lower flight time in lieu of the costs. The next type of rendezvous we looked at was a high Earth orbit rendezvous. So with this, you would use a cluster of Hall thrusters to put your heavier spacecraft into a high Earth orbit. You would rendezvous with your crew and then fly from there. So what you do with this scenario is you basically eliminate one of these delta Vs that you have to do with your chemical propulsion, with your nuclear propulsion, which is a lower efficiency propulsion. And we actually didn't see any gains in this. We didn't have very much gain from this, mainly because the time frame of our mission is such that the scaling really just doesn't work well for the EP systems that we looked at to do this. The next one is to actually have a separate cargo vehicle, which we send with some propulsion system to Mars. You meet up with that with your crew vehicle, and then from there on you perform your operations. Again, our cargo mission, the cargo that was not integral to keeping people alive, was not that high, the mass for that. So you really didn't get a lot of gain from that. You get maybe a 3-ton IM LEO, where I should have probably explained this, but IM LEO is the initial mass in LEO, which is what we try to minimize to get the minimum number of launches. So we don't get a very big gain from this. One that we did get a gain from, which we thought was interesting, was actually using this cargo vehicle to send some of our fuel for our nuclear thermal rocket along with additional cargo. So you see a pretty significant gain here, but the risk of rendezvousing with your fuel, which halfway through is something that we didn't think was enough to justify the cost that we gained from that. So we decided to just stick with the most simple, which was just taking a nuclear thermal rocket, launching it from LEO, and assembling everything and then launching it from LEO and flying with that. So here at the bottom is the reasoning, kind of what I went into a little bit. The small mass of the total system really, the small mass of the cargo is what really makes it so that EP is not very useful for what we wanted to look at. The time constraint really makes EP electric propulsion, which is what EP is, makes it difficult to use electric propulsion. And then, again, as I mentioned, the risks of fuel pre-placement was something that we're not sure about, but in a way we think it's a technology that would be really useful for eventual missions to Mars if we are able to place fuel there and then meet up with our fuel there, because it saves us a lot in delta V's that we need to have. Now that we've chosen our propulsion system, I'm going to give you a little information about that and the assumptions that we made in being able to use this. So first of all, we have to assume that we have zero boil-off because we're using hydrogen for our propellant. This is a decent assumption, we thought, and it's something that needs to be developed for future missions, and we think it's something that would be well demonstrated by doing this mission. We also have to have sufficient technology to actually use this, well, sufficient development to actually use this technology, so that's our second assumption. And then we basically ended up choosing a type of nuclear thermal rocket that is called the particle bed reactor. This is, if anybody's familiar with nuclear thermal propulsion, it is not a NERVA variant, which was some experiments that were done in the 70s. It is a little different from that, and it actually saves you a lot on mass. So to give you an idea of this propulsion system, we have the thrust ISPs, engine dry masses, and all of that fun stuff here. For engineers, numbers are fun, but these might not be so fun for everybody else to see. Here's just a basic layout. So you have this hydrogen which flows over this hot particle bed to give you a basic idea of how the particle bed reactor works. So now this is one of the really novel concepts of our engineering design, the Phobos Surface Explorer and the propulsion stage that goes with that. So you have to have a descent vehicle, which is how the actual explorer gets down to the Earth, not the Earth, but down to the moon Phobos, and then you have to have another vehicle which ends up sending the Phobos Surface Explorer Separator. I don't know these acronyms. I'm going to have to talk to somebody about it. But anyway, so you get this guy, and you have to have a propulsion system for both to make sure that you can get down and get back up. And we did design for that by ourselves. A lot of it was based off of similar designs which people have used, and if you're more interested in these, we're happy to chat about them afterwards.
Okay, now I'm going to talk about how to keep our astronauts alive and healthy. So by looking at analog studies and by just seeing exactly what our mission objectives was, we decided to take a crew of 4 astronauts in their 40s and of mixed gender. And in order to perform all of our science objectives, we need very specialized and trained, educated astronauts. So since this is going to be a very taxing journey, and since it is a precursor to Mars, we want to make sure that only those that are physically fit enough are able to undertake this journey. So also psychological testing will ensue. The psychiatric, diagnostic, and statistical manual will be evaluated, and anybody that shows any case of psychiatric disorders will not be selected as a crew member. Nira? So that eliminates a lot of people right away, probably including me right now. So this disorder right over here, neurasthenia, is something that's specific to astronauts in space, and it degrades their performance. So again, as I mentioned, we want individuals to perform at their peak, so anybody that displays any of these types of symptoms will not be able to participate in this exciting mission. Also, something that's novel will incorporate genetic testing. Some genes have been identified as having an individual become radiation tolerant. As was mentioned, we do not want our astronauts to die of radiation. Also, we decided our trajectory maximum time based on these radiation tolerances. So if we can select individuals that are even more radiation tolerant than the general public, we'll take them. Also, with the way that medical technology has been improving, we'd like to screen for future diseases, maybe probably see if somebody has a risk of obtaining a heart attack within the next 10 years. And also, something that was novel, we wanted to incorporate a final selection. So about 100 astronauts will be chosen by experienced astronauts. Maybe Buzz Aldrin could help us with this. And also, then these 100 candidates will be assessed in field test analog studies, such as Antarctic expeditions, wilderness training. And then these groups will sort of form into their own groups. They'll decide who they want to work with based on their positions up here, and the best performing group will be selected, as long as other factors as well. So radiation mitigation, this is the primary driver in taking humans into space. Our primary objective, as Ron Turner mentioned, was not to have a dose that exceeded the 3% excess cancer mortality risk. So by doing this, we're incorporating several assumptions, including a safe haven. So since we're launching during solar max, there's a higher chance that there'll be a solar particle event. So our dosimeters will be able to warn the crew of the impending SPE, and in case of that happens, the crew will right away go to the safe haven, and their dosage will be decreased. Additionally, we'll provide them with a water bed, so to speak, by having them sleep in water blankets. And since we're incorporating the Bigelow structure, the Bigelow structure is made out of this Vectran material. And as you can see here, it's primarily composed of hydrocarbons, which is a lower Z material, and it does not emit secondary radiation. We'll also be incorporating passive and active shielding. And there's a lot of proposed technologies within the next 20 years that can provide radiation shielding. But since we have high confidence that these technologies, we want to incorporate it. But we'll also be incorporating small testbed technologies such as photobioreactors that produce algae and that can recycle human biomass, just to see if they'll work for future experiments to Mars. So once, hopefully, if we've solved the radiation problem, we still have many other physiological problems to solve, one of which is bone loss. Bone loss, as you can see here, it's not uniform throughout the human body. So the human body that's affected the most, the parts, include those weight-bearing muscles, including the lumbar spine, over here the femur and the tibia. And also there's cardiovascular adaptation due to cephalic fluid shift. So in order to mitigate these countermeasures will be incorporated in the form of aerobic exercise, which will hopefully maintain the cardiovascular ability of the astronaut, as well as resistance training, which will provide impact to maintain muscles and bones in space. And also we'll be incorporating a short-arm centrifuge as artificial gravity, and we hope to understand the vibration mechanisms and incorporate a larger one and provide recommendations for a future Mars mission. We'll also be incorporating several other technologies. We just want to see exactly how these work during the long-duration mission. We're providing an exoskeleton that's been in the development for the past 10 years, and also the gravity loading countermeasure suit, which provides static loading throughout the human body. So if you guys were going on a road trip for, what our duration is, 456 days, what would you take with you if you know that you couldn't stop? Would you take Band-Aids? Would you bring a defibrillator? What would you take? So to answer this question, we looked at the Advanced Research in Space and Medicine Handbook, and this provided statistics regarding what is the highest risk and incidence. So based on that, we designed medical packs that will hopefully sustain astronaut life. And also a problem with taking medications in space is that they typically have a shelf life of about a year. And if they're exposed to radiation, then the shelf life decreases even more. So we'll be providing additional radiation shielding for the medicine. So for the telemedicine, the crew will not always have the opportunity to communicate with the ground. So we provided innovative tablet technology. We'll be training the crew extensively so they will know exactly how to diagnose themselves. And I'll also be incorporating sensors that they can place throughout their body, and it'll check it with a sort of database and compare it to symptoms and allow to self-diagnosis. Currently on the ground, there's 3D metal printing that has been incorporated. People can rapid prototype items out of powdered aluminum. So we'll be using our consumable wrappers from food to develop surgical tools, but we'll also be providing just major scalpels, scissors, things that can be incorporated in emergency scenarios. And as you can see here, it would be pretty cool to take a surgical room up in space, but as our propulsion guy stated, we're limited on mass. So we propose to take this inflatable surgical suite, which provides over here you can see a sterile environment. The astronauts just put their hands in, their wrists and feet will be restrained. This has already been tested in micro-G flights, and we're planning on taking it along with a magnetic strip over here that holds all your instruments in place. And here's laminar flow so that the area will remain decontaminated. So honestly, right now we don't really know what will happen to us. We don't know exactly what will happen to humans when they see this pale blue dot in space, which is the Earth. So our best guess has been from analog studies, where we can see where these studies have shown that although the individuals are healthy, they're not perfect, and they're prone to interpersonal conflicts, sleep deprivation. They can get bored, and even though they'll be going on an awesome journey, and sometimes there'll be problems with group dynamics. And as mentioned, we don't know what will happen when they see this pale blue dot, which is the Earth in the sky. So crew selection will help eliminate major psychological differences, because as studies have shown, there's a low incidence of major psychological problems in space. However, the crew will be trained on how to get along with each other. There's conflict resolution, where we will teach the astronauts that they don't always have to be right, and sometimes they and that sometimes it's better that both parties gain something, although you might not get exactly what you want. And for sleep deprivation, which probably our team could have used, which our team is experiencing this week, we recommend medication. However, the problem with this is that there are dependencies, so it's only recommended if there's if they have a major task that's coming up. And one of the major concerns is that they'll become, bored. If you're going on a road trip and you couldn't stop or do anything, just staring at the road in front of you, you get bored very fast. So we're planning on using innovative tablet technology so that they can read, play video games, and something that I wouldn't mind enjoy doing was skill training. Say, for example, if you wanted to learn a language, maybe half an hour can be devoted each day to learning Russian or Polish, whatever it is that you want to learn, or maybe even a type of electronic piano. And also, one of our major focuses is outreach activities. We want the public to know exactly what's going on, and we want to get them encouraged to do science and see the importance of exploration. So we'll be performing science experiments and communicating with the ground, and just having collaboration ensue from there. Also, studies on the ISS have shown that having a meal together, say for example there's a table, even though you can't sit at the table, you float around it, sort of brings some psychological benefits. And to keep them connected with the Earth, we'd like to provide virtual reality so that they will be able to perform things that they enjoy doing on Earth. Say for example, if they enjoyed snowboarding, we just input that program. We have 20 years to do it, and they can have fun that way. And also for family communication, it's really important they keep in touch with what's happening with their family. So we'd like to provide family photo albums, keep them interested in what's going on in that respect. So, although they're going to be happy, they need air to live, water to drink, and food. So this shows the major subsystems that feed into each other and how their lives will be maintained in space. So I won't go through this whole diagram, but I just want to show you a simple flow. So this over here shows wastewater that's ejected from humans, and it'll be filtered through this H2O water tank. And then the VP car additionally converts it to potable water. and then this will be fed back to the astronauts. So instead of bringing all the water that they'll need for this entire duration, we'll be recycling it. And there's several other subsystems that will be incorporated. So using the ECLSS software, we ran a simulation of if this environmental control life support system would work in space. And over here, as you can see, we decided to bring all the food with us. And we'll be testing some greenhouses, but we're not going to rely on that. And over here, you can see that they have sufficient water to maintain throughout the journey. And these fluctuations that you see are due to the conversion of human waste into drinkable water, as well as carbon dioxide conversion and another subsystem that will be used to keep their water clean. And as you can see over here, the CO2 remains at a non-toxic level. These are more conversions that are taking place so that they have available drinking water. And over here is also, as you can see, oxygen and hydrogen gas. So also to design exactly how they'll be living within this habitat, we incorporated personal crew quarters, avionics, a galley so that they can eat dinner together, and also an exercise room and centrifuge. And the way that we decided our volume is based on studies by the Celentano curve and also by a couple other proposed deep space habitats. And as you can see here, here's the hygiene, personal workstations, centrifuge, and the galley. Again, I guess you can tell I like to eat because I keep on talking about food over here. There's their dining room table and their personal crew quarters, which astronauts have mentioned that is very important to them, even if it's just a tiny box where they can put pictures of their family in. And with that, I'd like to take it back to Matt.
So we're running a little bit late on time. I'll make this quite quick. So back to the big picture. We're really looking at this as a stepping stone to get to Mars. This is part of a much larger program and part of a massive global context. And it's very important to remember that. So the risks are going to be high for any mission to Mars, but the gains are always going to be greater than the risks. The key, though, is that all of this is well communicated, because every single one of us in this room can agree on the fact that we should do these things. We should go to Mars. But we need to make sure that the entire world sees in the same light. So we started with a quote. I figured we would end with a quote. Ever since there have been people, there have been explorers, looking in places where others hadn't been before. Not everyone does it, but we are part of a species where some members of our species do, to the benefit of us all. There's a list of references. We have a ton more information you can read in our final report. We'd like to acknowledge our speakers, our mentors, everyone who's been around this entire week. It's been a fantastic week for us. We'd specifically like to thank Nick and Jason for all the hard work that they've really put into this, and all the sponsors as well. So thank you very much. If you have any questions, we'll take them now.
Members of Team Explorer, please come up to the front.
Did you have fun?
Yes!
We survived, so.
I was just one. In the end, near the inside there, you had your risk matrix up there, and it looked like it was populated with 10 risks. What were your top? Give me your top couple technical and safety risks.
Our couple of our top technical risks were the development of some of the vehicles that aren't in fruition right now, so there's a lot of risk with low TRL levels. We try to mitigate that by choosing stuff that's in development now. Also, if for any reason we had to do a flyby, like abort, then it would kind of put some strain on our mission. And then I don't know if anyone from the subsystems wanted to kind of highlight. I know we had some science risks with contamination that we were planning on putting in engineering design. And then, does anyone want to have anything to add?
Well, from human factors, radiation is one of the major concerns. And although, as Chris mentioned, some of the technologies have a high TRL number, they haven't been incorporated against solar max. So we could just make our best predictions and stay with LUCs.
At the same time, though, there are risks that we would also face on a Mars surface exploration, so that's what the purpose of this precursor is, to address those risks and see the effects and if we're actually affected by the radiation that the astronauts experience. So those risks are valuable to address on this precursor mission. That's why we chose to go with the route that we did.
Back to the radiation, on a slide, one of the bullets said passive and active shielding. Do you have an example of active radiation?
So okay. Yeah, so as passive radiation, we were thinking, first of all, the material we are going to use, we could use aluminium, so water and also hydrogen from the ECLSS system. These are components that we know they are good for radiation. And as an active one, we were thinking about generating a magnetic field. This is something that people have been talking about, but again, the TRL is really low, and before we didn't have the technology to do it. Maybe from here to there, we are able to generate our own magnetic field and then deflect the particles.
Yeah. But the Veltran, since it's composed of hydrocarbons, right now the radiation that it provides is comparable to that of aluminum. But beyond that, for additional protection, we're relying on these that, on the ECLSS system that we could strategically put throughout the cabin.
You mentioned the selection of the nuclear thermal, and I didn't get quite how much trade-off went into that, and I think you described it as enabling. What if you didn't have it? Should you just not do this mission, or is there was it just a way you could overcome the penalty with another approach?
I think it is possible, but from a almost number of launches standpoint, we thought this would be one of the best ways to go. You could do it with chemical, but your propellant mass fraction, I think, was higher than 99%, so you really have to have a lot of fuel. Electric propulsion systems can be used for this too. It becomes tricky. It's really a difficult problem. I wouldn't say that nuclear thermal is the only way to go, but I think it is a good way to go.
You said electric propulsion, that includes nuclear electric propulsion?
Yes, sir. And nuclear electric, I think, would be very enabling as well. It's also low TRL, so we didn't look too much into that.
And I think we have time for one more question. Dan?
Can you guys talk a little bit about your philosophy for redundancy? You had one explorer, surface exploring habitat, and your failure modes, and how you handle that.
So,
go ahead.
Okay, all right. So to explore the surface of Phobos, we actually initially started with two different options: a standard SEV, the concept that many are familiar with, and a new concept that we were trying to debate with. We wanted to leave some permanent architecture on the surface of Phobos for future missions for teleroboting, for example. So we really wanted to somehow leave some kind of architecture there, which is hard to SEV because it all comes back and then you just ditch it and there's nothing that stays on Phobos. So we imagined this type of modular SEV that would basically have all the functionalities of the SEV, for example, ascent back into the mothership, habitability, robot exploration, all sorts of functionalities, except it would be modular. It would be, each one would have a different function. So we actually went through a pros and cons analysis. We looked at mobility, a number of parameters, and we analyzed it. And we found that that solution was actually pretty dangerous. It had a really high risk in comparison to SEV. So the SEV was still a better choice, and it didn't solve our issue that we wanted to leave something on Phobos. So that's what led us to the two-stage SEV, where we believe that what we want behind the habitability, and the only thing we would come back would be the front part, which is the part for the ascent. And if you look closely, there were a number of redundancies that were built in that actually Chris thought about. The seat ports in the front section, the robotic robonaut that could call for help. There's lots of different functionalities of SEV that enables it to have a lot of different redundancies. So if an issue were to come up there, we'd be confident that a solution would be able to be thought of.
Yeah, it makes the mission really complex to have so many different vehicles, but it also kind of relaxes the risk on ECLSS failure because you have multiple nodes to take from.
Just to add into that, the ECLSS system has been designed with all redundancies. The analysis has been done only in the big habitat design, and we are supposing the 4 astronauts stay there all the time. To take into account maybe we have problems, we just can't land into the moon. So the design has been done like in this way, and all the hardware parts are redundant. So the ecosystem is really, really robust.
One quick thing to add to that, from a mission architecture point of view, we tried to sort of pick a mission architecture that reduced the risk as much as possible. So that's why we went with the opposition class mission, which is the shorter stay, as opposed to the conjunction class, which is longer stay. Because the longer you're out there, the more radiation, more likelihood that subsystems might fail. So we really felt that the shorter stay was enough to fulfill our objectives while significantly reducing the risk. And finally, we also looked at a lot of launch options with rendezvous in different places, and we found that a lot of the fancier rendezvous didn't really give us as much of a benefit in mass and other things, whereas that greatly increased the risk. So we're rendezvousing in low Earth orbit, and we're taking everything with us at all times. And so if at any time we needed to abort, we would have all the supplies and all the fuel for return trip.
Great, and let's thank Team Explorer one more time.